I'm going to talk about number systems like decimal, base 10, hexadecimal, octal, and binary. Later on, I'm going to focus more on binary because that's what digital systems are built with today. So the math behind the computers. So first, let's start off with number systems. How do we count things? So first, let's write down what we know. So you know that we count from 0 all the way to 9 using these symbols here, right? This let's do this is for decimal, aka base 10. So in general, we can say base whatever, right? And so if you count a number of symbols like 0, numerals 1, 2, it's 10, right? So hence the name base 10. Now let's do some math, right? So when you have these numbers and you start counting 0, 1, 2, 3, all the way up to 9, right? When you reach 9, what happens? What's the next number? So what's actually, you don't have any more symbols for that. So what do you do? It's okay, I'm going to reset this one. It's going to become the first symbol 0, and then I'm going to carry the 1. And you carry the 1 here and add there. So you got 10, right? And then you start doing over again, right? 11, 12, and so on, all the way to 19. And then what happens? You zero this one, so it becomes that, and carry the 1, right? Carry the 1 here. 1 plus 1 is 2, so you get 20. And it can follow that on and on all the way to 9, 9. And then what happens? Okay, zero this 1, carry the 1. Oh, this one is 1 plus 9, but we don't have any more symbols. What do? Zero it out and carry the 1 there. And then we got 100. Okay, so you get the point how to count, right? Now, let's talk about another kind of decimal. And by the way, we have 10 fingers, so that justifies us having that, okay? You should be able to see the whiteboard. Robbie, do you see the whiteboard? Yeah, so you should be able to see the whiteboard that I'm sharing right now. All right? I even shared the link there. If you don't see the whiteboard, try rejoining. Robbie, can you confirm that you see the whiteboard? Always, can you confirm that you see the whiteboard? Just say yes in the chat you can see, otherwise tell me if you don't see it. All right? Yeah, as I was saying, we have 10 fingers, therefore it's intuitive to count using these 10 symbols. All right, so the next one I'm going to talk about is base 8. That's called octal. And if you ever worked with permissions like in file systems like Unix, like chmod, that kind of stuff, they use kind of octal base. Now let's write out the symbols for that. So we can count from 0, 1, 2, 3, 4, 5, 6. Now how many of these do I got? And then 7. You can count them, you can get 8, right? So that's why it's called base 8 or octal. Now how do we count that? Let's try it again. Let's do the counting here. Let's see this one. Let me erase that. So, okay, so we're gonna count 0, 1, 2, all the way up to 7. Now we have reached the eighth symbol. Notice the octal doesn't have 8, doesn't have 9, those symbols. So what we do when we run out of symbols, the logic is you zero this out, carry the 1, so you get 1 0, which we call 10 in base 10, right? So that's how we count in octal. Does that make sense? And then we would go on saying, okay, from 0, if you add 1 is 11, 12, and then all the way up to the last symbol being like this. Now, if I increment that, I don't have any more symbols beyond the 7. So what happens? Zero that out, carry the 1, and then 1 plus 1 is 2. So we get 2, 0. And then you continue 2, 1, 2, 3, all the way to 7. And then what do we get after that? Dot, dot, dot. You got 3, 0. Okay. And then on and on. Does that make sense? So basically, when you run out of symbols, you have to zero out and carry the 1. That's how we count in any base. So if you got that for octal, you can get to any base. So it just, you have to understand how many symbols you got. Great. So with that, let's talk about hexadecimal. That one is more interesting because there's a lot of numbers in that. So hexadecimal base 16, aka hex. You ever heard that? You might have used that for memory addresses when you specify colors in CSS, that kind of stuff. And it's also useful because later we're going to learn that hexadecimal allows us to write binary very conveniently in a compact way. Now the symbols are 1, 0 through 9. And then because we don't have any more like kind of these numeral symbols to represent beyond the 9, we have to use letters. So you're going to see A, B, C, D, E, F. Okay. So if you count basically 10, 11, 12, 13, 14, 15, 16 symbols. Okay. So A is like 10, B is 11, C 12, D 13, E 14, and F 15. And you notice beyond 15 is 16, right? Which would make like, that's why we zero it out. That's why it's called base 16. So let's count in that one. So we would go here. Okay, we're going to start from 0, 1, all the way up to 9. Now, what do we do when we do 9? Do we still got symbols? Yes, we do. We got A. So from 9, it goes to A. And then B. And then when you add one C, and then when you add one D, and then E, and then add one F. Now, watch out. If I add one to F, I'm out of symbols. What do we do? Same thing. Zero this out, carry the 1. So we got 10. Okay. So we went from F to 1, 0. And then you start doing it again. 1, 1, 1, 2, all the way to 1, 9. And then you start doing A, then B, and then C all the way up to F. In that case, it goes to 2, 0. Okay, so from 1F, when you add, you zero the F, so it becomes 0, carry the 1, and add to the 1, and it comes to 0. Okay, so that makes sense? That's how we would count there. All right? Does that make sense? All good for everybody? Okay, so I'm sharing my whiteboard right now, so I hope everybody can see it. Now let's talk about binary. All right, so binary base 2. And can you guess how many symbols we got for binary? So binary, you got 0 and 1. So that's why, so these are used for computers. Any digital system today, electronics, computer stuff uses binary. And it's a sequence of zeros and ones, just two symbols. Very simple, very simplistic. That's why we call digital systems, because we have the digits 0 and 1. That's why when you talk about computers, you see these sequences of zeros and ones in the graphs and that people draw. Okay, so let's count in binary. So we only have two symbols. So 0, add 1 becomes 1. Add 1, what happens? I have ran out of symbols. So I have to 0 this 1, carry it, so that I get 1, 0, right? And then if I want to add one more, that's 1, 1, because the 0 at the right-hand side becomes 1. Now I ran out of symbols, so what happens? Okay, we got 1 here, 0 it out, carry the 1. But then we got 1 plus 1. You cannot have any more symbols. So you gotta, what? 0 it out, carry the 1. So in the end, you got 1, 0, 0. Okay? So you got 0, 0, 0, 1, 1, 0, 1, 1, and then 1, 0, 0, and then 1, 0, 1, 1, 1, 0, 1, 1, 1, and so on. Okay? You get it? So these are used for the computer because it's simple, and they found out how to build these numeric systems by simply having switches on and off. So if you could have something that is in a state that you can, maybe like a candle is on or off, right? Or a light or whatever. Could be even a glass of water. If a glass is full of liquid, that could be 1. If a glass is empty, it could be 0. So anything that you can imagine that has a state of being and not being allows you to build a information system. Okay, so that's why they chose this. And yeah, so let's talk about now how to convert between these bases mathematically. All right, so let's go down here. I'm going to scroll down. So let's start off converting 10 to any base. Let's say I have the number 6. Okay, number 6 in base 10. How would it convert that? Let's first do octal, base 8. So the way the algorithm works to convert to any base is the following. You take the number, you divide by the base, 8. This operation here, you get a quotient that I call Q, and you get a remainder that I'll call R. So 6 divided by 8 is what? I get a remainder of 6 and a quotient 0. So I take the remainder, write it down, and then the next time I do it, I'm going to take the quotient, and that's what I'm going to do, divide by the thing. But because it's already 0, that's when we stop. Okay? So 6 in base 10 is 6 octal. Now that might be obvious because we have the symbols 0 through 7, right? So it looks the same. Let's do something more, maybe more. Let's do 8. Notice there's no symbol for 8 in octal. So how is that base 8? So you take the 8, divide by the base 8. This division produces a quotient of 1, a remainder of 0. Now the remainder here, you're going to write it down as the number that you're forming, 0. Then the next time, what you're going to do is take the quotient and use that as the thing to divide by the base. That operation gives you a quotient of 0, remainder 1. So you take the remainder, copy it to the left of whatever we already have. You put it there. Then you take the zero and you would do the same thing again. But because it's zero, that's when we stop. So when a quotient is zero, we stop. And this is the number in base 8, right? Which makes sense. If you count 7, zero it out, carry the 1, and you get that one, 1, 0. So if you were to write an algorithm, you'd basically make a loop. As long as the q is not 0, you're gonna divide, and then you're gonna use the module operator to get the remainder, right? The integer division gives you the quotient, the module gives you the remainder. And then you would build the thing. And keep in mind that you always take the remainder and attach to the left-hand side at the beginning, not the end, right? Okay. Um, show the number 20 base 8. Okay, let's write that out. So you said you want a number 20, a base 10 convert to base 8. That's what you want? Okay, so we're gonna take 20, divide by the base. That's the first iteration. We got a quotient of what? And a remainder of what? So 2 times 8 is 16, right? So what is 2 times 8, 16, remainder 4? Is that right? And then you take the remainder, write it down here. That's the number that I'm forming. So far, the number is that. Now, the next iteration, we take the q as the number to divide by. And this will yield what? 0 quotient, remainder 2. So you take the remainder, add to the beginning. So n is going to be 2 followed by the 4. Okay. Makes sense? And then because the q is 0, stop. And then return n. So the 20, 10 is going to be 2, 4 octal. I write the number of the base here so you can differentiate. Okay, so that means 24 in base 8. All right. Um, let's try to do, so we did, let's do hexadecimal. So does anybody know about the, when you write CSS, you often see FF, right? What is that number? Let's, I'll show you. Maybe it's too big though. Let's try, let's start off with, let's see, 16. Let's try 23. Small number in base 10. It's what in 16. Later, I'm going to teach you the other way around, which is from any base to base 10. For now, let's just try to do this one. So algorithm is basically you take the number, divide by the base, which is 16 now. This will yield a quotient and a remainder. Remember, the quotient, you can use the slash when you do the code. The remainder is the percent for the module. So what we got here, 1 times 16, right? We cannot do 2. And that remainder is 4, 3 is 7, right? So write it down, take the remainder, write it down, and you always add from the beginning, right? As you're building this n number. And then you take the quotient and use that as the next iteration for the algorithm. And that gives you 0 for the quotient, remainder of 1. Take the remainder, put to the beginning of n. So n is now the 7 followed by the 1 on the left. Right? And then because q is 0 now, when q is 0, the loop eventually stops. That's the equivalent. You could have like while Q is not zero in your code, right? And yeah, so that's 1 7. So 23 in base 10 is 1 7 16. If you know later, I'll teach you that this is basically 16 plus 7, which is 23, because it's 1 times 16 plus 7 times 16 to the 0 power, which is basically 1. So it becomes 16 plus 7. That's how I confirmed that I did the operation right, because I know the reverse. Anyway, let's try binary. So let's do something like, I don't know, what's a good binary? Let's try 7. 7 base 10, what's it in binary? Base 2, right? So same thing. Take the number, divide by the base, which is 2. This will yield a quotient and a remainder. So this is basically 2 times 3, right? Remainder 1. So take the remainder. That guy is going to be added to the left at the number n you're building. Now take the quotient and use that as the next iteration. So 3 divided by 2. And then we got, what is this? Is 1, right? 1 times 2, remainder 1. And then take the remainder, add to the left. So the one that you had already, add it here, like that. Take the quotient, use it, 1 divided by 2. That's gives you what? It's basically 0, remainder 1. So remainder, add to the left. You already had 1, 1. So you're going to add 1 there from the remainder. And then you take the quotient, but because it's 0, stop. And then return this n. So basically the 7 base 10 is 1 1 1 base 2. And if I confirm later, I'll teach you how to do it. It's basically 1 plus 2 plus 4, which is 7. Makes sense. Anybody got it? Any questions? Does that make sense? You can write this in code, and it's basically a loop, right? While q is not 0, you're gonna take the number, uh, divide by the base, and then use the module percent to divide to get the remainder. And then you kind of add to the left of your string. Maybe you're doing string concatenation or something. N equals the R plus whatever n has. And then at the end, you return n. Okay, somebody said I want to know the reverse. That's what I'm going to get to next. All right, so we learn how to do one way, but what's the other way? From any base to 10. Okay, so the other way, let's try to do let's see the octal. So we did what in octal? 20, 20 is 24. So how did we get, if we are given 24? Sorry if I'm scrolling. So 24 octal, what is that in base 10? So what we do here is the following. The base is 8, so we're going to write it like this. You're going to write the powers of 8 from right to left, 8 to the 0, 8 to the 1, and so on. And then you're going to write the numbers like this. So we got the 4 on the right, we got the 2, and we could have gone on and on, 2 and 3, right? But those are actually just zeros. It's an implicit 0, right? So we don't care about those, so we don't usually write them out. So what we do is you're going to take these two, multiply, and then sum with the product of the other ones. So basically, it's the summation, if you know math, summation of all these i's from 0 to something, I don't know, k, of the a to the power k times the digit I. That's the mathematical writing for that. So let's do it. So you can do from right to left or from left to right. I don't know, whatever is convenient to you. So if I do right to left, so I'm gonna take, okay, got 4, the digit, right? Times a to the power of 0. And I'm gonna add to the 2, that's the other digit, times a to the power of 1. And if I do the math here, that's 4 times 1, because any number elevated to the 0 is 1. And then plus 2 times 8, which gives us 20 in base 10. Okay, so the 24 base 8 is 20 base 10. Does that make sense? So you take the digits, multiply by the power of the base, corresponding to its place as you write the numbers, and then you sum them all up. If you're a visual person, this is how I visualize it. I take these two, multiply, and then I add to all the other ones. Obviously, the ones with zero don't usually do it because obviously any number multiplied by zero is zero. So you can go on infinitely multiply by zero and adding it's going to give zero anyway. So we don't usually look at these. Okay, so let's try to do. So we did that one. Let's do the one for the 16, right? Because we had done 23 base 10 is 1716. So 1716. Let's do the opposite. 1716. So we're going to write the numbers down, each digit, and then above them from the right to left, I write the power of the base. So 16 to the 0. Maybe I'll do another color so you can 16 to the 0, 16 to the 1, and so on. We don't have any more digits, so I don't want to write it out. And then you do the same thing that we did before. Take the pairs, multiply, add to the other pairs. So 7 times 16 to the 0 plus 1, the other digit, times 16 to the 1. Do the math. That is going to give you 7 plus 16, which gives you, so you got 20 plus 4, 23 base. And is that right? We had done 23, right? Yeah, 23 here. So, right. Yeah, so as you do this more and more, exercising it, you're just gonna think in your head, right? You just wanna add up in your head. Let's do one binary. Did we do 7 binary? Was that what we had? What was it? 111 or something? Let's do a random one. Let's do 101, just for the sake of fun. This is binary. What's that in decimal? So in my head, I already know because what I do is my head, I'm just teaching my technique. I'm thinking like this. I put the 1 here, I put the 2, and I put the 4 because those are the powers of 2. 2 to the 0, 2 to the 1, 2 to the 2. So in my head, I'm already doing it. So, okay, I see the 1 here. So that's 1 plus, and then this one I ignore, plus 4 times 1. And that's when I get it, right? It's 5, right? Basically it. And binary is easy because there's only one digit, right? It's either 0, 1. So you either add the number itself or not, the power or not. There's no 2, 3, or whatever. Okay, so that's how I do it. Now let me do it the manual way, right? More, I just showed my thought process. So I write it down. I write the powers of 2 above. So the base 2, right? 2 to the 0, 2 to the 1, 2 to the 2. And like I said, you can already think of it simplified, like 1, 2, and 4, and so on, right? I remember 1, 2, 4, 8, 16, 32, 64, 128, 256, 512. I remember everything by doing it over and over, right? Anyway, Yeah, so just do the product of the digits with the power and sum them all up. So one, doing from the right to the left, 1 times 2 to the 0 plus 0 times 2 to the 1, right? I did this one just now. And then finally I do this one, which is 1 times 2 to the 2. Sorry, this is 2. And then we got what? 2 to the 0 is 1, so we got 1. 0 is going to be 0. And then 1, 2 to the 2, 4, right? And 1 plus 4 is 5, which makes sense. In my head, I had the 1 plus the 4, which was 5. All right, so if you understand this, it would greatly help you as you're doing those bit manipulation and binary questions in lead code, because you can immediately understand what the numbers mean. All right. Uh, so let me teach you something in the browser if you want to quickly find out how one number is written in another. So I'm gonna switch to my browser here and just share. So I have a browser open. I'm gonna open the DevTools, pressing F12, and I'm gonna click the console tab. So if you want to write a number that's not decimal in, for example, JavaScript, or it works pretty much for any language, they all follow the same kind of pattern. So I'm pretty sure it will work for anything other than JavaScript. So if you want to write a base 8 octal, you can start a number of 0, and then type the octal number, right? For example, if I had 7, 8, that would be 10, right? What's 10 octal? So 0 is meaning, it's basically telling, I want to write a number in octal base 8. And here's the number to the right. It's 1 followed by 0. What does that mean in octal? That octal 10, if you press enter, it means 8 in base 10, right? Because remember, if you had 7 and we had 1, 0 to 7, carry the 1, 1, 0. So that's basically 8. And you could test it out. Okay, what's 1, 1? Oh, that's 9 in decimal. What's 1, 2? And so on. You're going to see up to 1, 7, and there's no more digits. So the next one is going to be what? You expect it to be to 0, which is 16. What's following 15? That's how you write octal. Now, how do you write hexadecimal? If you might have seen this one in programming languages, 0x, and then type the number hexadecimal. For example, what is FF? I keep seeing FF in CSS. So if I type FF, oh, that's 255 in base 10. So that's what I mean. So if you do, I don't know, FCC, that's the base 10 equivalent. So you can see all the CSS values go from 0 to 255 because FF is the max. And for the red, for the green, and for the blue, right? So that's what it means. Comes from that. Now, how do I write binary? 0V. So if I want to write 101, which is the 5. So 0V means I want to write a binary number. Here are the digits, 101. And you get 5 in base 10, which we just confirmed before, right? Now be careful with this. You might get an error if you type an invalid number. For example, in base binary, there's no 2, right? So if you type 2, that make no sense. So you're going to get an error. Okay, now let me teach you how to convert from any base to other base. For example, the FF, right? It's written like this, so I put a parenthesis around it, and I say toString. This is JavaScript, by the way. Other languages might be slightly different. So if you want to convert, for example, from that to binary, you say 2 here, and that gives you that number's equivalent in binary. Okay, octal. What is the octal? You say toString 8. That's the base. That's 377. What's the decimal? 255. What's the hex? It's itself, so it's just gonna be FF. Okay, what's base 32? I don't know. So that's the number. If you're curious about using 32, not very useful. I don't know. We don't usually use 32, so anyway, that's how you convert from any base to any other base in JavaScript. So, but it might be useful to you if you're practicing. You want to quickly find out how one number is written with another without having to go through the algorithm doing by hand again. All right, does that make sense? Did you know about this? Comment out. How about letters in binary? There's no letters in binary, it's just 0 or 1, right? Binary can only have 0 or 1, no other symbols. Now let's talk about hexadecimal as related to binary, because that's very useful. So one moment here, Wesh. Show the whiteboard. I'm back to the whiteboard, so I hope you can see it. I stopped sharing my screen and now the whiteboard. So hexadecimal is base 16, and binary, they have very close relationship. And what is 16 in base 2, right? What is that number? 16 is 2 to what power? 2 to the 2 is 4, 3 is 8, and 4 is 16. Pay attention to that number. It's 4. It's going to tell you something. When we write memory locations, for example, it's very tedious to keep writing 0, 1, 0 like this. Very tedious. Imagine you have to keep writing on and on. So what people do is for every group of 4 binary, they write an X equivalent to make it more convenient to express themselves. Right? So when you see numbers, binary, you can actually write in hex. So that's very common practice. You write in hex. So this is base 2, this is base 16. So let's start from the right. 0, 0, 0. When you count 4, you group in 4, okay? So you're gonna take this and write it as base 16. Now this is basically just 0, right? So 0 in base 16 is also 0. And you have this one, then you're gonna treat it like, how do we convert this to, you know, well, I know that if I do like 2 to the 0, which is 1, 2, 4, all the powers here. 1 plus 2, 3, is 4, 7, 7, 7, 14, 15. So this gives me 15 in base 10, which is what in 16. Remember, 16, we have the 9, A, B, C, D, E, F. So it's F. So actually you can write F for that. Those, if you see 4 ones, it's F. And then the same here. Yeah, I see F. And then this one is what? 1, 2, 4. If I convert to 10, that's 1 plus 4, that's 5, base 10, which is the same in base 16. So these, how many we got here? 4, 4, 8, 16 were condensed to just 4. So you could just, when you write in memory, I don't know, you're dealing with memory locations, you can just say 5FF0. And that will be a lot more convenient than having to write all the zeros and ones when you try to express yourself. So there's this close relationship. And you've noticed the 4 here is what makes this possible, because 16 is basically 2 to the 4. So every 4 bits, you can group them as one symbol of hex. That's why you got that property. So very convenient. All right. Now let me talk about bits and bytes. What the hell is bits? What the hell is bytes? All these fancy numbers you might have known but never really thought about it. So bits is basically 0 or 1. So these are bits. 1, 2, 3, 4 bits. Now when you have 8 bits, 8, you call them, this group, a byte. Okay? So 8 bits, 1 byte. And that's where all the stuff comes from. It derives from this definition. When we got file sizes, like one character in a text file is usually 1 byte in length. That means that character is represented by 8 bits, right? Which leads me to information systems. Why do we use this binary stuff? Because you can build systems with switches that either are on or off, right? Like a lever. Imagine lever. Oh, you open or close. And they found out how to do it through electronics, right? Of course, you can do it manually. If you do it manually, let me think of a system to tell you, like an actual physical system that's can be used as an information. Uh, let's imagine we have these candles. Okay, these are candles. So the candle can be on or it can be off. So two states. So you can define, okay, when I see a candle off, that's 0. When I see a candle on, that's 1. Okay, so if you were to write, okay, let me put a candle here, another candle here. So I got these two candles and I'm going to put them all on. What does it mean? Well, 1, 1. So you can have many possibilities for this. Okay, let me talk about the possibilities. If you only have one candle, it can either be off or on, right? So two things, right? Off or on. So two, right? If you had two candles, how many states would I get? Well, I would have maybe the candle is two off. The candle is maybe the second is on. Maybe the first is on, but the second is off. Or maybe they're both on. I put this thing to say it's on. So, right, you can think of it that way. So you can keep four things. Now, if you notice the pattern, it had two candles, right? And each of the candles, each space, right? Think of it space. If you remember from math, like combinatorics, that kind of stuff, each space can be two possibilities, two possibilities. That means it's 2 times 2 available things to represent, which is 2 to the power of number of candles, right? So 2 to the 2 is 4, n equals 2. So we can have these four possibilities. Now you can represent numbers with these. Imagine the candles would represent numbers. So you can think of it as 0, 0, 0, 1, 1, 0, 1, 1. But these are binary. What about base 10? For base 10, since we have four values possible, we can only store 0, 1, 2, and 3, right? If you were to associate 0 of 0, 0, 1 of 0, 1, 2 of 1, 0, and 3 with 1, 1. But so if you add more candles, you can accommodate more numbers. So if you had 8 candles, right? 2 to the 8, what is that one? So 2 to the 10 is 10, 24, 5, 12. Is that 256? Did I do it right? Just confirm me there. So I can store numbers from 0 to 255, but I'm doing sign, right? Unsigned, sorry. No negatives, right? I'm considering only unsigned numbers. So that's why you see like CSS colors like this. And notice 8 is basically 8 bits, 8 bits, which translates to 2 hexadecimal values like FF for 255. So that's the relationship with hex. Okay, so you can build systems. Basically, if you had like 8 candles, you could put the candles and turn them on and off to represent something. Maybe you can represent the numbers from 0 to 55, and maybe the numbers could represent something like if all the candles are off, meaning, I don't know, maybe the system is okay, but then if you light, I don't know, one of the candles, like, and if the number becomes, I don't know, 123, that means system or somewhere in 123 there's a problem and you have to look into it. Maybe you have somebody looking at the candles, like this person who works in a factory, I don't know, imagine that he sees the candle, somebody turned on the candle that makes the number be 123. That means he has to go to, I don't know, pod 123 because there's a problem there. I don't know. I'm just making up some sort of information system, right? You get the point. So you can build systems with pretty much anything. This could be like a glass of water is empty, meaning zero. A glass of water is filled. And then you can grab 8 glasses of water and light them up. And if they're all in a certain state, that means one thing. You can make a table of what it means, right? And that's basically what computers do. They're programmed with all these states, right, that represent something. And that's all it is in a very simplistic form. Now, people found out they can build an information system with electronics, electricity, and that's the best way so far, right? How do they do that? They use a switch, basically on and off. And in terms of electricity, is the voltage, whether there's a voltage here or not. You can see in the graph if you see an oscilloscope, it's either on, meaning there's something up there, or off, it goes down, on, off. And today they use what's called a transistor to achieve that. Transistor, if you ever heard that. Transistor. It's basically a switch, electrical switch on and off. Because you can turn on and off things, you can combine a whole bunch of transistors to build an information system. Just like the candles, you had 8 candles, you can have 8 transistors, and they can represent something. Now, today we build the chips. There's probably billions. I don't even know the number of transistors. How many transistors in a chip today? So they've managed to find a way to pack all of these. So the number of transistors in a chip can range from millions to billions. They just did a search here. So that's how they build a system. They have so many of these that you can build all these states. Okay, and that's basically it, information system. And with these things, we can start building, like build you know, those logic gates, like and, or, not, and so on and so on. All right, and then you combine them to build like adders to do addition, full adder that takes the carry. And all of these is done by looking at the voltage, if it's on or off, on and off. So that corresponds to zeros and ones, right? And that's basically it. That's why they use zeros and ones for the systems in computers. Will that make sense? I'm going to open for questions if you have any.